Hi everyone. Today I'm going to tell you about a variant of my favorite problem, the multi-arm bandit. So what I'm going to do is that I will explain the basics of the multi-arm bandit, then tell you what is the variant that I want to consider, explain the new result there, and end with a lot of open problems. Everything presented here is joint work with Thomas Budzinski, and you can find the paper in the link below the video. In fact, we're not even going to talk about the bandit problem. We're going to talk about the simpler version, which is called prediction with expert advice, that corresponds to the full information case. So let me explain what this is. So you have K actions, 1 up to capital K, and to each action there is a certain performance associated to it. So you have P1 up to Pk. These are numbers in 0, 1, and they represent the quality of each of those actions. So if you select action I, then the quality, the typical reward that you're going to receive is going to be of value Pi. Okay? Now, in the full information setting, in this prediction with expert advice setting, what happens is that you observe at every time t, you observe a sample, let's call it LTI, which is simply a sample from a Bernoulli of parameter Pi. Okay, so what does it mean? This LTI is a number, it's either a 0 or 1. Oops, sorry. It's either a 0 or 1, and it's a 1 with probability Pi. So at every time step, you just observe passively realization for all of the action, and what you have to do is that you have to select one of the actions. So a decision is choose action, let's denote it by I sub t in 1 through k. Okay, and the reward that you get out of this is P I sub t. Okay, that's the reward that you receive. And you regret, you wish you had selected the action with the highest mean reward, which is the action with the max of the Pi. So your regret, let's denote it by little rt, is Pi sub t minus the max over I in 1 through k of the PIs. Okay, and the goal is to minimize the cumulative regret. Minimize capital RT, which is the sum of the little rt. T equals 1 to capital T. Okay, so the problem is clear. You passively observe IID realizations of K different distributions, K Bernoulli distributions. At every time step, given all the information that you have received so far, you have to select one of those actions, and you regret if you selected an action which is suboptimal, meaning there was another action with a higher mean reward. So it should be clear, I hope, that in this case, the most natural strategy is to simply select at every time step the action with the highest empirical mean. Okay, so you just select the action with the highest empirical mean. So strategy, strategy is going to be IT selected to be the argmax of P hat I. Okay, maybe Pi at T. Okay, so that P hat is just your empirical mean using all the observations that you have received on action I, and you just want to select the one with the highest empirical mean. Since empirical mean concentrates at rate 1 over square root t, up to a log factor, you know that RT is going to be bounded with high probability by something up to a log factor. I use O tilde to hide a log factor, 1 over square root little t. So this means that your total regret is bounded by O tilde of square root capital T. And this is very easy to be seen to be optimal. Okay, so super classical. Now, what are we going to be talking about today? We're going to talk about the two-player version of this. So 2 players So it's exactly the same setting. You have Alice and Bob, okay, and they each observe their own IID sequence. So Alice observes, let's say, LTAI, and Bob observes LTBI. Okay, so these are IIDs. The PIs have the same value for both players, but they just observe independent realizations. Okay, the way to think about it is that Alice and Bob, they live in the same world, but they have independent experiences in this world. Okay, so they won't see exactly the same thing, although on average they should see the same thing. Okay, now they play the same game. At every time step, they are going to select an action and they receive their mean reward, and they want to compare to the best they could have done in hindsight. And what's the twist? The twist is that if they collide, if they choose the same action, then they get no reward. Okay, so if ITA, let's say the action selected by Alice, is equal to ITB, then no reward. Okay, so in other words, your regret really in this case, little RT, just to clarify, is defined as PITA plus PITB, okay, the sum of the mean reward for the two actions selected times the indicator that ITA is distinct from ITB. And you compare this to the max over I not equal to J of PI plus PJ. And a key assumption that we're going to make is that Alice and Bob, they cannot communicate. Okay, so if they could communicate, this is a very easy problem, not very different from the one above. But here we're going to assume that Alice and Bob, they are playing the game, on their own. They are interacting with the same environment, but they cannot communicate at all. And I will explain the motivation for this. Okay, so the question is, can you get square root T regret with no communication? That's the challenge. Okay, and the answer is going to be yes, but the strategy is going to be very, very different, maybe from what you expect. Okay, so I hope the problem is clear at this point. Let me just briefly tell you one potential application. So application. So the application is in cognitive radio. Cognitive radio. So let me explain the application using more players. So let's say we have M players. Okay, and again, in this presentation, and in fact in the paper, we focus on M equals 2, but for the application, let's say we have M players, and this corresponds to devices. And what do those devices want to do? They want to communicate with a cell tower. This is a cell tower. And the devices, they want to communicate with the cell tower, and to do so, they can choose from K channels. So you have here K channels. These are the different actions. Okay, and K is larger than M. All right, so at every time step, what happens is that each device can choose a channel to try to communicate, but if another device is trying to communicate on the same channel, then the communication simply does not go through. Now, why do they observe IID realization from all those channels? Well, one possible motivation here is to just assume that those players, those devices, they can sense the channels. So asynchronously, they don't sense necessarily at the same time. They can all sense and get some kind of rough estimate of how good the different channels are. Now, given those estimates, they then choose a channel, but then the communication takes a longer time. So even though they are not synchronous, since the communication takes a long time, if somebody else gets on that channel while you're trying to communicate, it's going to kill your communication. Okay, so I think this is a pretty reasonable application. In fact, there are many papers trying to apply bandit theory to this cognitive radio. Okay, but now we're just going to talk about our very basic problem of this stochastic multiplayer prediction with expert advice. And we're going to focus on M equals 2 players, as I said, Alice and Bob. And in fact, we're even going to make a further assumption that K is equal to 3. Okay, that's what we're going to do. So we have 2 players, 3 distribution, P1, P2, P3, that you don't know. And at every time step, we get Alice and Bob get IID realization from those 3 distributions, and they just want to coordinate and make sure that there are no collisions, even though they cannot communicate. Hence the title, Coordination Without Communication. So let us see what is the challenge. Okay, so the challenge. The challenge is as follows. Given their observations, they each have an ordering on the actions. So given observations, let's say that Alice is such that P hat A, okay, so the empirical mean for Alice, let's say that action A1 is bigger than P hat A of action A2, which is bigger than P hat A of action A3. Okay, and these are all at some time t, little t. Okay, so there A1, A2, A3 is just an ordering of the 3 actions given the empirical observations. So from Alice's perspective, given the information that she has seen, she believes that action A1 is the best, action A2 is the second best, and so on and so forth. And for Bob, we're going to denote it by B1, B2, B3. Okay, so the naive thing to do would be that Alice, and of course it should be A1T, okay, just to B1T, etc. So the naive thing to do would be that Alice plays action A1 and Bob plays action B2, right? They don't want to collide, so they certainly don't want to both play the best action, but maybe they agreed beforehand that Alice will go for the best action and Bob will settle on the second best action. But there is a very simple problem here. The problem is that P1 could be equal to P2, could be equal to P3, for example. In this case, there is just no best action, and which one is the best empirically is just basically a coin flip. So in that case, there will be a constant change of a collision. Okay, it will be really bad because with probability basically 1/3, Alice will think that action 1 is the best, and with probability 1/3, Bob will think that action 1 is the second best. Okay, so there is a probability 1/9 of a collision. All right, but you might argue, okay, but in this case, you know, it should be that they recognize that there is some ambiguity on what's the best. So maybe what you want to say is, you know, Alice will go with the best empirical action if there is no ambiguity that this action is really the best. And if there is ambiguity, then maybe she will go just with the lexicographic order. So let's say, for instance, P1 is equal to P2 is much better than P3. Okay, so action 1 and action 2 are the same quality, but they are both much better than action 3. So then Alice and Bob, they will both agree that action 1 and 2 are the best, but they don't know which one is the best among the two. So then they could agree that in this case, if there is ambiguity, Alice will go with the lexicographically first. So in that case, Alice would play action 1 and Bob would play action 2. But the problem is, again, that you have to set a threshold. You have to say at which point do you set that there is no ambiguity. And then there will be, in turn, once you set this threshold, there will be a tuple P1, P2, P3, such that whether you declare ambiguity or not is again a coin flip. So geometrically, what happens is the following. So geometrically, what happens is that our strategy for Alice and Bob, it's really a mapping sigma from the empirical means. So what are the empirical means? For Alice, the empirical mean is a point in the cube 0, 1 to the 3. And for Bob, it's another point in this. So our mapping is from 0, 1 to the cube squared to 1, 2, 3 squared. Okay, with certain constraints so that there are no communication. And really what happens, actually it would be better to just, sorry, let me just explain this a bit better. It's really you have sigma A and sigma B, right? You have a mapping from empirical observation for Alice and one for Bob. And the question is, how do the boundaries of those maps interact? Okay, and I'm going to draw those boundaries and explain more generally why there will always be an ambiguity issue, and then explain how to fix it. Okay, so that's the plan. Because it's annoying to draw in dimension 3, I'm going to make a further assumption to draw in dimension 2. Okay, so draw in dimension 2. Let's assume that P1 plus P2 plus P3 is equal to 1. Okay, let's assume this is known to both players, and it's easy to relax this assumption. But this will allow me to draw a picture. Okay. All right, so I hope we're clear on what we're doing. So now I'm going to explain why there will always be a problem to coordinate without communication in this setting. And then I will explain how to fix this problem. Okay, so let's draw. So now, okay, this is my space of tuple P1, P2, P3. And because I assume that P1 plus P2 plus P3 is equal to 1, really what I have is I have a simplex. So let me draw it like this, where this point, it corresponds, let's say, to 1, 0, 0. Okay, so this point means that action 1 has a probability 1 of giving a 1, action 2 has a probability 0 of giving a 1, action 3 has a probability 0 of giving a 1. Okay, so along this direction, action 1 is the best. Okay, it's becoming better and better. Here at the center, we have 0, 0, 0. Okay, nobody, sorry, not 0, 0. We have 1/3, 1/3, 1/3. Okay, at the center, everybody is equal, and since the sum is equal to 1, they are all equal to 1/3. Here, let's say this is a point 0, 1, 0, and here is a point 0, 0, 1. Okay, I hate when it does that, but all right. So now, what happens? What happens is that in this region, let's say we have P1, P2, P3 here. In this region, this is the truth. Then what happens is that Alice and Bob, they are going to observe 2 points in this two-dimensional plane, which are very close to this point. Namely, there will be a little ball here, and this is of radius O tilde of 1 over square root t. And maybe Alice will see a point here. This will be P hat of Alice. And Bob will see a point here. This will be P hat of Bob. Okay, so again, the truth, the real world is the same for both at this point. But their experience in this world is slightly different. It's IID realization, so while they are not too far from estimating the truth, there is still some distance between them. Okay, very good. So now let's see what happens in this, let's say in this region over here. What happens is that the best two actions, it's action, you see 2 and action 3. Okay, so in this case, the best two action is action 2 and 3. In here is going to be action 3 and 1. Okay, because you have this 1 here. And in here, in this region, the best is action 1 and 3. Okay, so let me try to re-explain this, redo this picture. Okay. Let's try to do it again. So it's like this. Again, here it's 1, 0, 0. Over here it's 0, 1, 0. And over here it's 0, 0, 0, 1. Okay, so in this region, what we want to play is action 2 and 3. In this region, what we want to play is action 1 and 3. In this region, what we want to play is action 1 and 2. Now we have these two maps, sigma A and sigma B, right? And sigma A is, again, if the truth is here, this is a truth, then maybe Alice observed a point here, this is P hat A, and Bob observed a point here, this is P hat B, and the difference between the two must be at most 1 over square root T. Okay? So sigma A is going to tell me for each point here, which action should I play. So let's make just a choice. Let's say that sigma A in this region is going to be 1, and sigma B is going to be 3. Okay, so in this whole region over here, where we really want to play action 1 and 3, we're going to say Alice play action 1 and Bob plays action 3. Now notice that when you approach this boundary here, what happens is that if the truth is here, then it could be that Alice falls on one side and Bob falls on the other side. So you need some consistency when you go across boundaries like this. So to have consistency, since I want to play action 1, 2, here I should still have Alice that plays action 1. And I'm going to say that Bob plays action 2 here. That way, you know, if I don't know which side I am on the boundary, okay, then Alice doesn't need to know which side she is on the boundary. She will always play action 1. And Bob will try to figure out whether he's on this side or that side and alternate between action 2 and 3. Okay, but over here, anyway, around this boundary, action 2 and 3 have the same value, so it doesn't matter too much. Now, let's see what happens around this boundary. So around this boundary, we want to play action 2 and 3. So Bob should remain on action 2, and Alice can play action 3. Okay, so this is what we're going to play here. Now let's see, when we cross this boundary, we want to play action 1 and 3. So Alice should stay on action 3, and Bob should play action 1. But you see, there is an issue now. There is a problem here. In this region, we started by saying we want to play action 1, 3, and now I say we want to play action 3, 1. Okay, so this is the basic topological abstraction of this problem. Why coordination without communication is really hard? It's because of this. Because at some point, there will be some inconsistent decision to be made. Okay, and we have to fix this problem. So the way we propose to fix this problem is as follows. So our idea is to keep the picture as it is right now, but we are gonna add a random interface. Okay, so let me make an assumption. So assumption, I'm gonna assume shared randomness between the player. And I will remove this assumption, okay? I will remove this assumption, but let me assume for the moment that I have shared randomness. So what I'm gonna do now is that I'm gonna pick a random angle theta. This is a random angle theta. And what I will do is that this will be a random interface along which I will make the move from 3, 1 to 1, 3. And the way I'm going to do it is as follows. I'm going to move from 3, 1 to 1, 3 by going counterclockwise. I will do 3 1s and 3 2s and 1 2s and 1 3. So geometrically, it's very simple how to do that. I will just extend this interface. So let's draw it like this. Like that. So what happens is I continue this region of 3, 2 all the way here, and I continue the 1, 2 region all the way here. Okay, so again, just to clarify, it means that here Alice still plays action 3, here she plays action 1, and Bob here plays action 2, and then he plays action 2 here. Okay, and then after that, right, it's 1, 3. Okay, so this is how I move. I move from 3. So Alice, she does 3, and then she moves to action 1, and then she stays on action 1. Bob's move from 1 to 2, and then stays on action 2, and then move from 2 to 3. So basically, they never move at the same time. Okay, and of course, what is going to be the width of this? The width of this thing is going to be 1 over square root t. Why is that? It's going to be so that the two observations, they never cross more than one boundary. So it could be that the truth is, let's say, here. And then the two observations, maybe Alice observes a point here and Bob observes a point there. But it's never going to be that Alice observes a point all the way two boundaries away from it. Okay, very good. So now that's great, but there is a big problem here. And what is the big problem? The problem is that in this region over here, you see that, let's see, is that correct? That the region that I want? Yes. Let's say this region here, 3, 2. I'm not playing action 1. And action 1 is among the best. Okay, I'm playing action 2, but action 2, look at that. Action 2 is terrible. Action 2 was good in this direction, but now I'm all the way over here where action 2 is very bad. Okay, so let's see what happens. So let me do a smaller version of this. Okay, and we have this random interface, theta. Okay, and let's say the truth is here. And let's denote this distance by delta. And over here, best was 1, 3. But we play in the random interface, we play, let's say, 2, 3. So that implies a regret of delta. Okay, but the probability that my tuple P1, P2, P3 is in the interface, what is it? Well, I'm at distance delta and I'm choosing a random angle, and the width here is 1 over square root t up to a log. So the probability that I fall in within delta away from this random interface, that I fall at distance 1 over square root t from this random interface, which is at distance delta, is 1 over square root t over delta. So the probability of this, this probability times the regret, the product of the two gives me 1 over square root t. So on average, my regret from this random interface is only 1 over square root t. Okay, so the conclusion is that my regret is O tilde of 1 over square root t. So my cumulative regret is O tilde of square root. So this gives you a shared randomness strategy with regret square root t, and which has no collisions between the two players. Now you can de-randomize this strategy. So de-randomization. So the de-randomization is simply to make the interface dynamic. So instead of having this random angle theta, you can have an angle theta that depends on time t. So the interface will move during the game. And then instead of saying that for any fixed point here, let's say the probability of falling in the interface is, bounded by basically 1 over square root t. You're going to say that you're only in the interface a fraction of the time 1 over square root t. Okay, and everything works. So at the end, the theorem is that there exists a deterministic strategy for Alice and Bob with regret O tilde of square root t and no collisions with high probability. So at this point, there are many, many open problems. Let me mention some of them. So first, for single player, in this very simple scenario, you can get log t regret, log t over delta, where delta is a suboptimality gap between the worst action and the second best. Can you get that for 2 players? Okay, so that's the first question. I don't know if you can get log t. Then in bandit, so I didn't really explain what is a bandit problem, but in bandit, instead of passively observing IID samples from all the action, you only observe a sample from the action that you played. You can generalize the strategy that I explained, but the de-randomization does not work. So in bandit, the question is, what can you do without shared randomness? And that's a really good question to which I don't know the answer. And then, of course, here you saw that I did only the case of k equals 3, m equals 2. The generalization to higher k and larger m is highly non-trivial, but we have something already that we're going to write up at some point, but it's much harder. And I think that's all I wanted to say for today. Thank you very much.